afternoon, friends. It's my last class for my favorite course, flight mechanics. Really, I feel very happy that today is my 66th class, and I am in last class after so many months. I have able to complete this lecture. You know that I am in the process of teaching the flight mechanics. This flight mechanics is for the 4th semester of aeronautical students. I am Dr. Yagya Duttta Dwivedi, professor from Institute of Aeronautical Engineering, Hyderabad, India. Today I will be discussing about question bank solutions, safety requirement, takeoff and the landing performance, which is the module 5 in our syllabus. So in this I will be discussing derivation of takeoff performance, effect of thrust, effect of drag, effect of ground friction, effect of density on the landing. Question bank discussion I will be doing. So first question I am taking that discuss about takeoff performance of an airplane. Give a sketch for different distances used for takeoff distance. So what is a takeoff? Takeoff can be constituted as a flight maneuver during which an aircraft is accelerated from stop, that is V0, and after rolling on the runway for a short period of time, a couple of 10 to 60 seconds, it becomes airborne and initiate climb. There are 3 stages of that takeoff. First is the ground roll or the ground run. Then we have the transition or the rotation, and then airborne. So if you see here in this diagram, from here V is equal to 0, and from here V take off. From here it is called the ground roll. From here it is a SR, that is the transition or the roll. From here to here it is a climb, and it is clearing the obstacle, and obstacle is 50 feet or 15 meter. It has to climb. So this the VG, that is the ground roll plus transition distance plus airborne distance. The summation of this thing is called STO. S takeoff is equal to SG plus SR plus SA. So this is the basic concept for the aircraft takeoff on the ground. What are different phases of the takeoff distances? Explained with suitable diagram. So takeoff is one of the most demanding phases of the flight. The aircraft engines are typically operating at a maximum rating airspeed or low, so control is minimal. So if you see here from this diagram, distance is 0, V is equal to 0. It is the ground roll distance. Now you reach to the rotation. In the rotation, we have the V is equal to VG, S is equal to SG. Now from here, S is equal to SR. From here, the angle of attack is increased, but these wheels are still touching. In this zone, wheels are still touching on the runway. From here, it is a transition distance. In this, your climb angle is initiated. Your S is equal to S transition. From here, it is climb started, and it is the S climb. So it has to clear 50 feet obstacle. Then only it is assumed that first one is the ground roll distance SG. Velocity corresponds to SG is VG. VG is a lift off velocity, that is V lift off, corrected for the wind, that is VG is equal to V lift off plus or minus V wind, and for a tailwind it is subtracted for a headwind. Plus is aiding for the tailwind, and for the headwind it is subtracted. The lift off velocity is typically expressed as some factors above the aircraft stall speed. We will use V lift off is equal to 1.1 V stall. What is the landing performance? Landing is another very demanding phase of the flight. As with takeoff, the landing is operating at airspeed near the stall. Precise control of the flight path is important to assure a touchdown at the desired point on the runway and with a minimum sink rate. Another challenge involved in landing is dissipating the energy of the aircraft once on the ground to bring it to the stop. Landing performance is very dependent on the pilot's technique. Discuss about the landing. This is also known as a go-around, missed approach, or the discuss about discontinued landing. It is coming, and as it is approaching, it is told to take off. So this is known as a go-around or missed approach or wave off landing. In aviation, a go-around is an aborted landing of an aircraft that is on final approach. A go-around can either be initiated by the pilot flying or requested by ATC for various reasons such as unstabilized approach or an aviation. A go-around is an aborted landing of an aircraft that is on final approach. A go-around can either be initiated by the pilot flying or requested by ATC for various reasons such as an unstabilized approach or an obstruction on the runway. If a pilot determines by the time the aircraft is at the decision height for a precision approach or missed approach point for a non-precision approach, that is, the runway or its environment is not in the sight, for that safe landing cannot be accomplished by any reason, the landing approach must be discontinued or a go around, and the missed approach produced must be immediately initiated. What is bulk landing? How go around is done? The way the bulk landing term is generally used is that the actual landing procedure has begun and must be aborted. A go-around generally begins at a higher altitude and lacks the urgency of the bulk landing. In the bulk landing, it is a very urgent. It is about to reach to the runway. But go-around is much higher than the before the decision height. Aircraft has to abort. That is called the go-around. But if it is very near to the runway, or sometimes it is about to touch and then has to take off, that is called the bulk landing. Bulk landing climb is a go-around from a below decision height, possibly in the flare. Note that all engines are assumed available, assumed required gradient on. Go-around thrust in all engines, landing gears down, landing flaps set. So these all things are done. So now I will go for the sixth question. Derive the expression for the ground roll distance. So here I have shown here the runway here. In this runway, aircraft is parked here. Now engine is started. From here it is moving and up to here. Then it is SR. SG is a ground roll distance. SA is a acceleration distance. SR is a rotational distance. SG is a ground roll distance. And this SG is equal to SA plus SR. We know that acceleration phase SA distance, F is equal to MA, M is equal to W by G, A is equal to dV by dt. So W by G, dV by dt, for V we can write V minus V headwind. Assuming headwind is a constant, so dHW by dt is equal to 0. So this is equal to W by G into dV by dt. Now sum of the forces is in the direction of the V. We can see that W by G dV by dt is equal to, in this is equal to T minus D minus FR. So let us look dV by dt term here. So dv by dt term, so dv by dt is equal to dv by ds into ds by dt. By the chain rule, ds by dt is equal to vg, that is the ground velocity, which is v minus vhw. So here dv by dt is equal to v minus vhw into dv by ds. So here w by g, v minus vhw dv by ds is equal to t minus d minus fr. So now ds by dv, now if we invert this thing, ds by dt, this will be w by g, v minus vhw divided by t minus d minus fr. Now to integrate this to find the total distance. So integration, this ds is equal to w by g, v minus vhw divided by t minus d minus fr into dv. Integration from I to I plus 1. So I to I plus 1 ds is equal to w by g, I to I plus 1, v minus vhw divided by t minus d minus fr into dv. Apply for the several points, that is the now next we have to about the thrust drag. So we got this equation, this is the distance equation, and if we see here we have different terms, that is the thrust drag and fr. These things we will be discussing in the next questions. Discuss each term like thrust frictional force related to the takeoff distance equation. So here first we will be discussing about the discussion on the thrust. So here we have the turbojet, piston turboprop and the turbofan. So T and V, if you see for the turbojet, it is like this. For the piston, it is falling down as the velocity is increasing, the thrust will decrease. For the turbofan, it is a parabolic equations, parabolic line. So we have derived that SA is equal to SI plus 1 minus SI is equal to W by G, VI to VI plus 1, V minus VHW divided by T minus D minus FR dV. So assuming that T and V variation is parabolic, for case 3 here, this one, case 3, so T is equal to T naught I plus T prime I V plus T double prime I V square. Here T naught, T prime and T double prime can be obtained by experimental. Only for the turbofan, following the parabolic relation with V square. So this equation is for turbofan. Now if we discuss about the friction force Fr, this Fr is equal to mu r W minus L. So this is equal to mu r W minus half rho V square SW into CL. Assuming CL is equal to constant, mu r is equal to 0.04 to 0.1, that is the gross landing, and 0.1 for the smooth. So 0.04 for the smooth landing, smooth runway, and 0.1 for a grass runway. Next question, discuss each term like drag force related to the takeoff distance in the distance equation. So drag is the force acting to the direction of the flight. Drag is a force acting opposite to the direction of the flight V, and we know that drag D is equal to half rho V square S CD. So half rho V square S CD is equal to CD naught plus CD naught L into CL plus 16 HW by pi BW CL square divided by 1 plus 16 HW divided by pi BW whole square pi EAR. This here is called the ground effect. So ground effect also plays very important role on the aircraft, and here if your aircraft wings are very near, that is this HW is equal to less than or equal to BW, then ground effect will be experienced, and this ground effect will generate normally at the wingtip. We have the wingtip vertices. These wingtip vertices are creating the drag, reducing the lift. But if the aircraft is near the ground, these wingtip vertices will be dissipating like this, like this. They will not circulate, and aircraft will be getting the benefit. So here, this term is the ground effect term, which is written here. So assuming that T is a parabolic, so now SA is equal to W by 2G VL square divided by T minus D minus FR, where VLO is equal to lift off, and it is 1.1 Vs, where Vs is equal to under root 2 by CL maximum under root W by SW by rho. So VLO is equal to 1.1 under root 2 by CL maximum under root W by SW rho accelerated. So now we got here SA is equal to 1.21 W square divided by rho GSW T minus D minus FR 0.7 V lift off. This is the final equation of accelerated distance. So this here we got the SA for this equation. So now we have to find out the rotational distance SR. Rotational time range from 1 to 4 seconds. 1 is for the general aviation aircraft and 4 for the large aircraft. So SR is equal to VLO minus VHW into TR, where TR is the time. Keeping VHW is equal to 0 at the no wind condition, SR is equal to VLO into T. So here SR is equal to 1.1 into TR under root VLO is equal to under root 2 by CL maximum under root W by SW by rho. So we can write here that ground roll SG is equal to SA plus SR, and if we sum up, we will get 1.2 W square rho GSW CL max T minus D minus FR 0.7 V lift off plus 1.1 TR under root 2 by CL maximum under root W by SW by rho. This is the ground roll distance equation. CL maximum, this roll, tail dragger will have more CL maximum, taken less SG. So if it is a tail dragger aircraft, the aircraft which have the like this is the tail dragger aircraft, CL maximum is more, it will take less distance. Question number 9. Briefly discuss the space available and space required for landing of an aircraft. Explain about each parameter and its importance. A runway of at least 6,000 feet in length is usually adequate for aircraft weigh below approximately 200,000 pounds. Larger aircraft, including wide bodies, will usually require at least 8,000 feet at sea level and somewhat more at a higher altitude. So if you are flying at higher altitude, more runway is required. At the lower altitude, less runway is required. If the small aircraft up to 6,000 feet, nearly 2 kilometers, and if it is bigger aircraft, 8,000 feet or somewhere nearly 2.5 kilometer range is required. Explain the effect of flight variables on the takeoff performance. Name all necessary flight variables for this condition. So we know that this SG is equal to 0 to VR mv by T minus mu mg minus half rho V square S CD naught plus mu this thing dV. These also here. Velocity is important. Thrust is also important. Mu mg, that is the frictional force, and the drag force and the lift force, all are important parameters, and as per that our ground distance will be calculated. If you have the more thrust, then SG will be reduced. If you have the more velocity, SG will be reduced. So like this we have to find out. So this is the last lecture. So I have mentioned here end of the course. Really, friends, I am really very grateful for you all for very nice cooperation. Lot of viewers have seen and lot of comments I have got as of now. I really want to thank my management of Institute of Aeronautical Engineering, also the principal Dr. LVN Prasad, for giving me this opportunity so that I am able to perform all the lectures in a given time. It's really great to be here. I'm really thanking from my bottom of my heart, and please do appreciate my work and also like and subscribe my channel. These are the references here: Aircraft Performance and Design, International Edition, McGraw Hills, SL by EME, Aircraft Performance and the Practice, AIA Education Series. Any questions, you are welcome to us. yddwivedi@gmail.com. Thank you very much for the joining, and we hope this will work nicely. And till then, goodbye and see you for the next course very soon. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.